In this system design series, today we are going to look at system design for key value store. So key value stores are distributed hash tables. A key is generated by the hash function and should be unique. In a key value store, a key binds to a specific value and doesn't assume anything about the structure of the value. A value can be a blob, image, server name, or anything that the user wants to store against a unique key. Usually, it's preferred to keep the size of value relatively smaller, KB to MB. We can put large data in blob store and put links to that data in the value field. Key value stores are useful in many situations, such as storing user sessions in a web applications and building NoSQL databases. Examples of key value store usage include bestseller lists, shopping carts, customer preferences, session management, sales rank, and product catalogs. Now, here are the following key design topics that we'll cover as part of the key value store design. First, we'll design the overall key value store and we'll look at the requirements for a key value store and design the APIs, scalability and replication, scalability using consistent hashing, and there are other methods to do that, and replicate the partition data, versioning data and achieving configurability, resolve conflicts that occur due to changes made by more than one entity and will make our system more configurable for different use cases, enable fault tolerance and failure detection, make a key value store fault tolerant, and how to detect failures in the system. So before jumping into the high-level design of key value store, it's always good to start from the customer point of view. We should ask, okay, what is the motivating use case? Why are we building this key value store? Once we get a sense of it, then we can, start probing further into the motivating use cases. Here I have listed a few questions to ask, depending on what response the interviewer gives around the motivating use cases. Some of these questions would be applicable. So, for example, what is the service interface going to look like to customers? Since it's a key value store, there's going to be get, put, and optional delete APIs. Is versioning supported? Is it single region, multi-region? Is it a specialized key value store for any specific kind of workload? When I say specific kind of workload, is it going to be just, is it predominantly write once, read many times? Or is it going to for session management or kind of memcache kind of use cases or Redis kind of use cases? Then is key expiry supported? Are we supporting TTLs? Is it on-premise or cloud? Security? Do we need to make any assumptions about the data? Any compliance related requirements? Encryption? Do we need to support at rest or in-transit encryption? Any durability promises we should be aware of? Is the system any consistency promises or guarantees that we need to be aware of? Replications, are we going to support tags? Batch operations, in the sense, are we going to support operations that involve like multiple key and values? Data integrities, are we going to support checksums? And then any key value attributes and ranges in terms of, be it kind of, it could be size, or the kind of naming requirements, kind of data or kind of values that customers are allowed to store in this key value store. So once we have identified some of these key requirements and what interviewer is kind of interested in, we can take it from there. So typically there'll be some core functional requirements. From the API perspective, we are going to have a put, get, and delete. Put means given a key and value, I should be able to reliably write the data to key value store. Get, given a key, I should be able to get the latest value against the key or corresponding to the version specified with the key. and delete. I should be able to delete a specific key, and given a version ID, I should be able to delete that specific version. There'll be some non-functional requirements or goals for the design. The design should be scalable. As the system, as the use of the system grows, we should be able to horizontally scale the system. Availability, the system should be highly available. If customers are relying on this for critical workloads, so they expect high availability and high scalability. Even during spiky traffic, our system should be fault tolerant. The key value should operate uninterrupted despite failures in the servers or their components. So once we have nailed these functional and non-functional requirements down, we can jump into a high-level design. So before that, on the scalability and replication, so as I talked about the scalability is important because over the time the usage of these systems grows, and as the usage of the system grows, I should be able to kind of add more servers and horizontally scale the system. So on the scalability part, one naive way to kind of scale the system is let's say we have a number of nodes. So we get a request, and we take the hash of that request, and we mod by the number of servers that we have, let's say m here. And whatever we get, we'll get the value between 0 and m-1, and we direct that put to that specific node. Now, that mod approach doesn't really work because if we remove that any node, then the keys will be redistributed and availability will be kind of a question mark, or it will put kind of pressure in the downstream services. So what else we could do? We could have consistent hashing. It's pretty popular approach. It's an effective way to manage the load over the set of nodes. In consistent hashing, we have a conceptual ring of hashes from 0 to n-1, where n is the number of available hash values. We use each node's ID, calculates its hash, and map it to the ring. We apply the same process to request. Each request is complete by the next node, then it finds moving in the clockwise direction in the ring. When a new node is added to the ring, the immediate next node is affected. It has to share its data with the newly added node while other nodes are unaffected. It's easy to scale since we are able to keep changes to our nodes minimal. This is because only a small portion of the overall keys needs to move. The hashes are randomly distributed, so we expect the load of the request to be random and distributed evenly on the average on the ring. So a picture will make it clear. So as you can see in this diagram, there are 4 nodes on the ring. So the node n1 came, it went through the hash and it was placed on the ring. Similarly, n2, n3, and n4. Now the request comes and it falls between n2 and n3. So if you look at clockwise, it will be served by n3. The primary benefit of consistent hashing is that as the nodes join or leave, it ensures that a minimal number of keys needs to move. However, the request load isn't divided in practice. Any server that handles a large chunk of data can become a bottleneck in distributed system. This is a well-known thing. That node will receive a disproportionately large share of data storage and retrieval requests, reducing the overall system performance. As a result, these are referred to as hotspots. A trick we can employ to address the hotspot is use of virtual nodes. We'll use virtual nodes to ensure that more evenly distributed load across nodes. Instead of applying a single hash function, we'll apply multiple hash functions onto the same key. Let's see an example. So suppose we have 3 hash functions. For each node, we'll calculate 3 hashes and place them in the ring. For the request, we use only 1 hash function. Whenever the request lands onto the ring, it's processed by the next node found while moving in the clockwise direction. Each server has 3 positions, so the load of the request is more uniform. Moreover, if a node has more hardware capacity than others, we can add more virtual nodes by using additional hash functions. This way, it will have more positions in the ring and serve more requests. So as you can see in this diagram, the nodes are hashed with three hash functions and placed on the ring, and then the request comes. We use only one hash function, the hash one, and then it lands between the green and the purple node, and then it will be served by the purple node looking at the clockwise direction. Now, advantages of virtual nodes. If a node fails or does routine maintenance, the workload is uniformly distributed over other nodes. For each newly accessible node, the other nodes receive nearly equal load when it comes to back online or is added to the system. It's up to each node to decide how many virtual nodes it is responsible for, considering the heterogeneity of physical infrastructure. For example, if a node has roughly double the computation capacity as compared to others, it can take more load. So in the primary, secondary, or primary, it's also called primary backup, leader follower, what else? Master slave, but it's not used anymore, unlikely so. So in a primary secondary approach, one of the storage areas is primary and the other storage areas are secondary. The secondary replicates this data from primary. The primary serves the write request while the secondary serves the read request. Let's be careful here. The primary can also serve the read request. So for example, if you want to provide read your own write guarantees, then the user which writes to the primary can also do a read, and it will get the most updated value for the key. But if there is a synchronous or asynchronous replication going on, depending on, like, if there is a synchronous replication, then the read can happen from any of the secondary nodes. It will provide strong consistency, but the downside is the writes will be costly because the primary has to wait acknowledgement from all the sync replicas before it can send an ACK to the client saying the write was successful. So after writing, there is a lag for replication. Moreover, if the primary goes down, we can't write into the storage and becomes a single point of failure. The second is chain replication. So in the chain replication is a new approach. It's actually not new. It's been around since 2004. It's an approach to coordinating clusters of fail-stop storage servers. The approach is intended for supporting large-scale storage services that exhibit high throughput and availability without sacrificing strong consistency guarantees. So in this approach, there is a chain, there is a head of the chain, and then there are replicas, and the last replica is known as the tail. So the writes or updates happen at the head, it propagates through the chain to the tail, and all the reads happen at the tail. Now, in the original paper, the reads could only happen at the tail, and the writes could only happen at the head. As you can see, the downside of this approach was the tail, had a limited throughput because the read couldn't be served by any other node. So in a more updated paper, the read can be served from any other node, and to facilitate that, what happens is, as the write propagates through the tail sends an acknowledgement to the head through all the intermediate nodes that, okay, the write is kind of successful. So then each replica ensures that it has the most updated version of the value, and then it can serve the read. Now in a scenario where, let's say, as you can see in the image, a write request comes kv2, so it gets written at the head, it goes to the second replica, and it gets written over there. But before it can propagate to the second replica, the third node, a write request, a read request comes for k on the second replica. So the replica contacts the tail asking for, okay, what's the latest value or the most durable value for this key is, and tail replies is v1 because the tail has v1, even though the replica has v2. The v2 is considered dirty as when the request came because it has not propagated to tail. So because the most durable version is v1, the replica responds with v1. Okay, let's look at the API design. Ideally, we should cover put first, but here we are looking at get. So get we can have different kind of variations of get for the key value store. In one version, we can have a get, and given a key, it returns the latest version of the value, or if it is not version, it just returns the value. If the service supports versioning, then the other API could be key and optional and a version ID. In that case, the get returns the value corresponding to that version ID and key. So the second is put. This function finds the node where the value should be placed on the basis of the key and store the value associated with it. The context is returned by the system of the get operation. If we have a list of objects in context that raises a conflict, we ask the client to resolve it. In general, the context is the metadata. So the API takes a key, a value, and the metadata and stores it reliably. The metadata, there will be some system metadata like the creation date, last update, and some could be user-defined metadata. The user-defined metadata, one data that could be helpful is TTL if it supports expiry. The other could be tags. If you want to tag your key value, that could be helpful. So one of our kind of functional requirements was that the system should be configurable. Well, it was not technically a requirement, but yeah, that's nice to have. We want to control the trade-offs between availability, consistency, cost effectiveness, and performance. So let's achieve configurability by implementing the basic get and put functions of the key value store. Every node can handle the get and put operations in our system. A node handling a read or write operation is known as a coordinator. The coordinator is the first among the top n nodes in the preference list. I mean, this configurability, I mean, we can have a client written which, which customers can use to do their gets, put, delete, or if they want to list their keys, they could use the client library to do that. So this is, this we can skip. Yeah, so in this slide, I talk about the quorum. So generally, once you do a put, how many nodes should acknowledge that the write is kind of successful before it sends a okay to the client. So generally there is a nice formula with the read, write, and number of nodes that are involved in the quorum. So let's consider two variables, R and W. R means the minimum number of nodes that needs to be part of the successful read operation, and W is the minimum number of nodes involved in a successful write operation. So if R equal to 2, that means our system will read from 2 nodes when we have data stored in 3 nodes. We need to pick values of R and W such that at least one node is found between them. This ensures that the reader should be get the latest written value. For that, we'll use a quorum style quorum-like system by setting R plus W equal to n and greater than n. What it means is if you're setting, let's say, n equal to 5, then R could be 3, W equal to 3. So what it means is you have 5 systems, 5 nodes involved in your quorum, and then when you do a write, if any 3 of those 5 nodes responds with okay, you send to all 5 the put request. If any of three of them say okay, I got the data, then the master says okay, or like the coordinator node says okay, I'll consider the write as successful, and it returns to the client saying okay, your write is, or your put is durably restored. Similarly for the read request is sent to all 5, and the first 3 that responds with a value, the coordinator sends to the client okay, here is your value corresponding to the key that you told me to get data for. Fault tolerance and failure detection. Typically, distributed systems use a quorum-based approach to handle failures. A quorum is the minimum number of votes required for a distributed transaction to proceed with an operation. So if a server is part of the consensus and is down, then we can't perform the required operation. It it affects the availability and durability of our system. We could use the sloppy quorum instead of a strict quorum membership. In the sloppy quorum, the first n healthy nodes from the preference list handle all the read and write operations. The n healthy nodes may not always be the first n nodes discovered when moving clockwise in the consistent hash length. Anti-entropy with Merkle trees. Each node keeps a distinct Merkle tree for the range of keys that it hosts for each virtual node. The nodes can determine if the keys in a given range are correct. The root of the Merkle tree correspond to the common key ranges is exchanged between the two nodes. And we'll make the following comparison. Compare the hashes of the root node of Merkle trees. Do not proceed if they are the same. Traverse left and right children during recursion. The nodes identify whether or not they have any difference and perform the necessary synchronization. So once we have clarified and scoped the problem, discuss the requirements, the high-level designs, and various aspects of the system design, we should leave some time at the end to do a design check. The design check is primarily to ensure that whatever design we propose matches the original requirements. And then we should point out some key health metrics, some testing strategies, any security, if it is applicable, how we are going to do a security review of the system. It's also called threat modeling. What are the different threats the system could have, in what ways it can fail, and then deployment if it is applicable, debuggability of the system if things go wrong or things fail, how soon we will know, and what metrics we will use to keep ourselves informed, and any extensions to the design or to the overall service. So that should conclude the design for this service. Hope this was useful. Have a nice time. Like and subscribe for more such content. And if you have a design you want me to cover, do mention that in the comments.